Yeah, thank you. Okay, good afternoon everyone. So yeah, let's do a quick recap of what we have done. Right, so we have proved a bunch of things in the last few lectures. And essentially we are done with pretty much all of the proofs until this point in the book. Modulo whatever we skipped, but that's actually quite a tiny fraction. Right, so let's just recall quickly. Right, so we are all quite familiar with the three polytopes being considered, right? So the smallest one is the perfect matching polytope, the main object of interest in some sense. But then we look at its relaxations, the tight cut perfect matching polytope, where you include all the degree constraints, if I may call them, for all tight cuts. For any tight cut, you want the sum to be equal to 1, which will anyways happen in the perfect matching polytope. Therefore, it is a proper subset of the tight cut perfect matching polytopes, right? And then we considered a further relaxation, which is the so-called fractional perfect matching polytope, or if you like, you can call it the Birkhoff von Neumann polytope, where you have just non-negative 10 degree constraints, the two obvious constraints, right? So that is the most relaxed one of the three. And turns out that these two polyhedral creatures are directly related to graph theoretical notions. So it turns out that if you want the polytope to be exactly equal to the tight cut perfect matching polytope, then that is exactly the same as saying that the graph is solid. Every separating cut is a tight cut. Whereas if you want all three to be the same, right, in particular you want the perfect matching polytope to be equal to the fractional perfect matching polytope, then it turns out that's exactly what we call Birkhoff von Neumann graphs. That's the definition. So either the graph is going to be bipartite, which means 0 bricks, or it is a near brick, which means 1 brick, and that unique brick naturally has to be solid or Birkhoff von Neumann. Like intuitively it makes sense. Right? It would be strange to have a brick that is not solid, but that is not Birkhoff von Neumann, but the graph being Birkhoff von Neumann. So intuitively you would expect if the graph is Birkhoff von Neumann, then the unique brick is also Birkhoff von Neumann. Right? And in the case of bricks, let us appreciate the fact that solid Birkhoff von Neumann are the same, and they are both the same as being free of odd conformal bicycles. Right? In fact, we proved more generally that Birkhoff von Neumann is the same as free of odd conformal bicycle for all matching covered graphs. Right? Therefore, also in the case of bricks. And yesterday, what we did is we proved the equivalence of these two. Right? Again, one direction holds for all matching covered graphs. Birkhoff von Neumann is a subset of solid, whereas in general, solid is a superset of Birkhoff von Neumann if you consider all matching covered graphs. So for the 1 implies 2, that is where we assume the graph is a brick. Whereas for 2 implies 1, we did not actually use that. Right? We proved a more general statement. So the Venn diagram in general is you have the solid graphs, inside which you have the Birkhoff von Neumann graphs, and inside that you finally have bipartite. Yeah. Good. And let's go back to the decision problem. I don't know, you can call it dp solid, dp Birkhoff von Neumann, doesn't really matter. Given a matching covered graph, decide whether it is solid, decide whether it is Birkhoff von Neumann. Turns out they are both equivalent because you can just compute the bricks and braces, or you don't even care about the braces, just compute the bricks and polytime. Right? That can be done because of ELP. And then you just have to check how many bricks there are and whether the brick is Birkhoff von Neumann or not. Okay? If all the bricks are Birkhoff von Neumann, well, that means that the graph is solid. In fact, that is if and only if. And if there is only one brick and that brick happens to be Birkhoff von Neumann, then the whole graph is Birkhoff von Neumann. Otherwise, it is not. Right? And of course, the bipartite case will just say yes. Right? No need to compute bricks if the graph is bipartite. Right? So the point is, both of these, now I can just raise a decision problem. Instead of talking about matching covered graphs, I can just say, given a brick G, decide whether G is solid, which of course is the same as being Birkhoff or null, right? And there are many ways to see why this problem is in co-NP. Right? At this point, we have multiple ways of looking at it. Can someone suggest one way to say it is in co-NP? There are at least 3 ways, I think, now. So if I want to convince you that a graph is not solid, a brick is not solid, or it is not Birkhoff or null, same thing. What do I show you? Odd conformal bicycle, right? I can just show you conformal odd bicycle, that is one certificate. So that would settle this, that would put it in co-NP. What's another certificate? Non-trivial separating cut. I just throw a non-trivial separating cut and done. Yeah, you can check that the 2 contractions are matching covered. And that's not difficult. So that's another certificate. What's the third one?
From the definition of Birkhoff.
Yes. You will give me a vector and you need to give me
an odd cut.
You have to give me an odd cut for which the Edmonds constraint is violated. Yeah? So that is the third one, right? The fact that the vector satisfies non-negativity and degree constraints is not difficult to check. Check. And I gave you the odd cut, so check that the sum across that cut is less than 1, right? So therefore we now have 3 co-NP certificates for this problem, 2 graph theoretical, 1 not as graph theoretical, one could argue, but still works, right? So clearly the problem belongs to co-NP for 3 different reasons. It's not known to be in NP and therefore also not known to be in P. Is it in NP? Open. Is it in P? Open. Yep. Okay. Questions, concerns? In some sense, this is the first. I think this might be the first decision problem we are discussing in this course. Or have we talked about other decision problems so far? I mean, of course, you can ask, given a graph, decide whether there is matching covered brick or bricks, all those things you can do. But in some sense, this seems to be the first sort of characterization problem in matching covered graphs that we are discussing in this course, if I'm not mistaken. Right? Okay. But of course, there are many more problems. We'll talk about them eventually. So there are 2 more things I want to discuss from Lucchesi-Murty. One is, let's talk briefly about separating cut decompositions. It is exactly what you think it is. Instead of tight cuts, you choose a separating cut and take the 2 contractions and you keep doing this. What will the result be? In the end, when you can't find any more non-trivial separating cuts, what are the graphs you have got? Solid bricks and braces. The result of separating cut decomposition is a list of solid bricks and braces. Right? In some sense, if you basically what you can do is, if you like, you can just do tight cut decomposition, and then on the result there you can do separating cut decomposition. Well, the braces will not break further, right? Because and the bricks will give you solid bricks, but possibly also bipartite graphs. Let's do a quick example, right? So. What do you get here? If you do a separating cut decomposition or a conveniently chosen separating cut decomposition, what will you get? 2 copies of K4 and 1 copy of K33. Right? That's basically how I constructed this graph. I just sliced the K33 with K4 on one black vertex and with K4 on one white vertex. You can check that both of these are separating cuts, and you will get K4, two copies of K4 and one copy of K3C. In this graph, I don't think there is any other separating cut decomposition possible. You can confirm later. But in general, you can have multiple applications of the separating cut decomposition procedure, and then the same question arises: is it unique? Is the result unique? Right? And clearly this is more general than tight cut decomposition. We proved that in the case of tight cut decomposition, the result is unique. Right? So if it were true here, we would have proved that actually. So since we did not prove that, you can guess what the answer is. The answer is no, it's not unique. Here is an example. I'll just draw the graph and ask you all to figure out two different this is the famous tricon graph. We'll talk about this later, but maybe someday. But this is not what I want. Here is a nice graph. Can you all try to figure out, find two different applications of the separating cut decomposition procedure whose results are not the same, not even up to multiplicities of edges. Yeah? So, okay, let me know if and when you figure it out. Right, so it looks like everybody found at least one particular set of pairwise laminar separating cuts. This set. Pretty much, I think everyone has found this one. And if you apply these separating cuts, then you are going to get 3 copies of K4. Sorry, 4 copies of K4, my bad. Yeah, so this one will give you 4 copies of K4. This particular application. Turns out there is one more application, at least one more application that I am aware of, and I'll give you a hint for the other one. We have proved that if there is an odd cycle, if you shrink the complement of the vertex set of an odd cycle, that is always matching covered. Shrinking an odd cycle may not give you a matching covered graph, but shrinking the complement of an odd cycle always gives you a matching covered graph. You may find that useful. In fact, not only will the graphs not match, even the number of graphs you get will not match. Okay. Number of solid bricks is not an invariant. Okay, final hint. You need only one cut. There is a cut here, that is a separating cut, and both the contractions will be solid bricks. Then you cannot do anything more. See if you can find that cut. And the previous hint was, if you see an odd cycle, remember shrinking its complement will always give you a matching covered graph. That has a nice consequence. If the graph has two vertex joined odd cycles that span the entire vertex set, we can call it a spanning odd bicycle. Then that cut separating the two cycles is a separating cut. Can you find a spanning odd bicycle? Of course, it doesn't tell you that the two contractions are solid bricks, but well, that happens in this case. Right, so the final hint is find two vertices joined 5 cycles. If you can find two vertices joined 5 cycles in this graph on 10 vertices, the cut separating them will be a separating cut, and in fact that works. Right, so it's this one. This one is a separating cut. The two contractions are W5 up to multiple edges. Two copies of W5. Maybe I'll put star, star. Okay. Sorry? One is simple, I think. Are both of them simple? No, this one won't be simple because here the 5 cycle has more edges. Wait, maybe you're right. Maybe it's both simple. No, I'll get a vertex of degree 5.
Oh, okay.
I don't think they're simple.
Oh.
They're not simple. No. Yeah. Yeah. But anyways, the point I want to make is that the separating cut decomposition procedure need not give you a unique list of solid bricks and braces. In fact, not even the numbers may match. As you can see, here we got 4 creatures, here we got only 2 creatures, right? So, yeah, things are not as good, which is partly why separating cut decompositions have basically found no applications in matching covered graphs so far. Although Lucchesi-Murty do mention that who knows, maybe there is something, right? Maybe at some point we'll find that separating cut decomposition procedures are useful. Maybe you take I think they make a statement like, amongst all such applications, the one that gives you minimum number of solid bricks and braces, maybe that has some relevance, but we don't know. Like, it's all speculation at this point. So separating cuts have found uses, and that is a lot because of Carvalho Lucchesi-Murty's work. They have found a lot of applications of separating cuts and solid graphs, which are the ones solid bricks especially, where there are no non-trivial separating cuts, right? But not the procedure itself. The procedure itself has not really found any real applications. Okay, so good. Yeah, so that's one point I wanted to make. The other point I want to make is I want to go back to this point, being free of odd conformal bicycle. Right, so this is not the same as saying being free of an odd bicycle. The conformality is very crucial. But let's just recall, at some point we discussed this class of odd-intercyclic graphs, right? So odd-intercyclic graphs so this I can talk about I don't need matching code or anything, I can just talk about graphs. Any graph that is free of odd bicycle. Yeah. So that means there are no two vertices and odd cycles, or equivalently any two odd cycles share at least one vertex. Of course, bipartite graphs are odd intercyclic graphs because there are no odd cycles. Right? So it turns out that there is actually work on odd intercyclic graphs. So if it were true that odd intercyclic was the same as, let's say, Birkhoff or Neumann in the case of bricks, that would actually give you a polytime algorithm. The problem is it's not the same. And the smallest counterexample, as I mentioned earlier, is the Murty graph. Right, so this is a brick. If I'm not mistaken, this is the smallest brick that is Birkhoff von Neumann. That is not odd intercyclic. Yeah. Yeah. I think it's the smallest one. Right? So this is the problem. The conformality is what is creating the problem. That being said, there is some history that I would like to convey to you, and also I would like to tell you very vaguely and without getting into too many details about this characterization of odd intercyclic graphs. So yeah, let's see how to do this. So we have talked a lot about planar graphs in SGT, right? And in some sense, the plane is the only surface that I have any understanding of. But there are other surfaces. And for those of you who have taken a real course in topology, you may probably know much more than I do. But I will still try my best to convey whatever little I understand. And this brings me to how many of you have wondered what this figure is about? The figure on the cover page of Lucchesi-Murty. Yeah, have you thought about it? Do you know what it is about?
Some embedding of some graph in the projective.
Yeah, it's an embedding of something in the projective plane. So let me tell you a little bit about the projective plane. Anybody who is already familiar with the projective plane? Yeah? Yes? No? 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 Okay, okay, fine. So, not a great figure. Okay, so, okay, so there is, maybe I'll actually read a few things from Bondi and Murty. Actually, there's a reason I asked for Bondi and Murty, not just the cover page, but there is a bit more. I would like to read out verbatim. So if you go to chapter 10 of Bondi Murty, there is the planar stuff that we talk about. And then there is a section 10.6, surface embeddings of graphs, that I never discuss. So I'll just read out a bit from that. During the 19th century, in their attempts to discover generalizations of Euler's formula and the four-color conjecture, discussed in the next chapter, graph theories were led to the study of embeddings of graphs on surfaces other than the plane and the sphere. The plane and the sphere are of course the same. In recent years, embeddings have been used to investigate a wide variety of problems in graph theory and have proved to be an essential tool in the study of an important graph theoretic parameter, the tree width, whose theory was developed in an extensive series of papers by Robertson and Seymour. The books by Bonington and Little, Fresher and Fan, Gross and Tucker, and Mohar and Thomason, I am only familiar with the last one, Mohar and Thomason, have excellent accounts of the theory of embeddings of graphs on surfaces. We present here a brief account of some of the basic notions and results of the subject without proofs and without making any attempt to be rigorous. Okay? So, in that spirit, so think of, I want you to imagine a surface, this is basically like the plane, but there is one key difference. This is called a projective plane. Okay? So of course any planar graph I can just draw here in this little space over here because we are drawing finite graphs, right? So I can just make a small enough drawing and fit it here. I can't draw K6 without crossings. But maybe if I allow myself some flexibility over here, then maybe I can draw K6. So what is the flexibility I'm going to allow myself? I'm going to think of it like a lot of video games actually do this. In a lot of computer games, you go out somewhere and then suddenly you come out from some other place in the screen. Do you know that? You've seen that in those games, right? So think of it like that. Every point on the circle is identified with its antipodal point. Okay? You're going to think of this circle. The only point I want to make is that this point is exactly the same as the diametrically opposite point, also known as the antipode. Okay? So I want to draw K6. Let me show a drawing of K6, which is directly from Borneo and Murty. I'll put three vertices here. It's K6, so I'll connect them. I'll put one vertex here, which is the same as what I see here. These are the same vertices. This is 0, this is 1, this is 2. I'll put one vertex here. Sorry, not here. I'll put one vertex here, which is the same as this fellow. I'll put one vertex here, which is the same as this fellow. Yeah, that was right. Okay, good. Okay, so let me label things so that you know which one is the same. Okay, 0, 1, 2, opposite to 0 I'm going to put 4, and this is also 4. Okay, both of them are 4, both of them represent the same vertex. Opposite to 1 I'm going to put 0, 1, 2, why am I putting 4 here? It should be 3. My brain is not able to process things. Opposite to 1 I'll put 4, and this is also 4. And this is 5, and this is also 5. Okay, fine. I want 3, 4 and 5 to be adjacent to each other. So what I see here, this is the edge joining 3, 4, but this is also the same as what I see here, because each point here is identified with its antipode. This point here is the same as this point here, right? So this line that you see here, it represents the edge joining 3 and 4. But because of the identification, it's the same as this one. Yeah. So I also have 3, 4 and 5 adjacent because of these lines that you see. Now I need to make 5 adjacent to 0, 1 and 2. I need to make 4 adjacent, 3 adjacent to 1, 2 and 0. I need to make 4 edges into 0, 2 and 1. Yeah, this is K6. Because of the duplication of vertices, you see 9 vertices. But in reality, it's 6 vertices. Okay? This is K6 drawn on the projective plane. Right? So we call this a projective planar embedding of K6. Because in this drawing, no 2 edges meet except at a common vertex, just like planar embeddings. Right? This projective planar embedding of K6. Yeah? Fine? Yeah.
More like you are having an edge on the to other side of the sphere.
Yes,
Right?
that's right.
Their crossing is allowed. We are not.
Yes, we are using that flexibility of the surface. Yeah. Another thing you can try is you can try to draw K5 on a torus. So torus is a different surface. Torus is basically like your donut or vada, whatever you like, right? So the point is there's a nice drawing in Lucchesi-Murty actually. Maybe I'll pass it around to show it to you because I don't think I can draw this. Yeah. Can you pass this around? Torus. Okay. For example, on a torus, you can draw. Pass it around. Especially those who are not too familiar, right? You can draw K5, for example, on a torus without crossings. Okay, you can try that later. You can buy a vada and try to draw it. It might be easier to buy vada than donut here. Yeah, okay, good. Okay, so this is a projective planar embedding of K6. So it turns out that odd-intercyclic graphs, there is a characterization for them. Apparently, this was known to many people. I'll actually read out from Lucchesi-Murty this time. Yeah. Subject to some connectivity conditions, every odd-intercyclic graph turns out to be a projective planar graph of a special type. I have not described the type yet. I'll describe it soon. This has been known for a long time to many prominent mathematicians, but no proof was ever published. Eventually, a paper by Kawarabayashi and Ozeki, which appeared in 2013, gave an elegant proof of this result. They showed that if G is an internally 4-connected graph, I don't know what internally 4-connected is, I think at some point in my PhD I read about this, then G is odd-intercyclic if and only if G satisfies one of the following conditions. I'm going to skip the condition, you can read about it later. Right? So they gave a complete characterization of odd-intercyclic graphs. And because of their work, you can actually decide in polytime, if I'm not mistaken, whether a given graph is odd-intercyclic or not. Right? Maybe you need some connectivity conditions, but that should probably not be an issue for the original decision problem. That should just be like a reduction. So let me show you now projective planar embeddings of Mobius ladders. Remember, Mobius ladders are odd-intercyclic. We never proved it, but let's look at a drawing of Mobius ladders. Okay. So, this is my projective plane, and now I want to draw a Mobius ladder. I will draw M8, which is a solid brick. Not bad. I need to join 0, let's me label 0, 1, 2, 3, 4, 5, 6, 7. Yeah? In a Mobius ladder, you join the antipodal vertices. Well, that sounds nice. That's convenient. Antipodal. I want to join 0 to 4. One way to join 0 to 4, I can go here, but maybe I will just utilize the flexibility of my projective plane. I come out here and I go and finish here. Yeah, this is the same edge. Let me call this E0. E0 goes from 0 and goes to 4. This is also E0. Now I want to join 0 goes to 4, 1 goes to 5. E1, E1, E2, E2, E3, E3. Yeah, that's a drawing of the Mobius ladder on the projective plane without any crossings, right? So this is a this is also famously called the Wagner graph. Okay. And now let's pay attention to the bound lengths of the faces. We haven't talked about faces yet. Now we'll talk about faces over here. So this is a face. Yeah. And what is its length? Length is 8. Yeah. Face of length 8. This fellow, this stuff here is the same as this stuff here. This whole thing is one face. Yeah, all of these points are the same points as these points. And this time it is not an edge. Here they were actually edges. This time this is not an edge of the graph. Right? Okay? So all these points are the same as these points. That was this one is the same face. So whatever this face is, F0 maybe, is the same as what you see here, F0. Let me see, is that correct? What is the length of this face? 4. How many edges do you see in the boundary? You see 0, 1, you see 4, 5, and you see E0 and E1. Same edge, 2 edges, right? So total length is 4. And now you can see by symmetry, this will be another face of length 4, F1, which is the same as F1. This is another length face, okay, F2, F2, length 4, length 4. I mean, I'm writing twice because I don't need to write twice. Let me just write once. Okay, F2 is 4, F1 is 4. This is F3, length 4. Yeah. This is a projective planar embedding of M8, and every face has even length. Yeah. There are no odd faces. Turns out, such a graph is always going to be odd-intercyclic. If a graph G admits a projective planar embedding with 0 odd faces, then it is odd-intercyclic. you can try to convince yourself later, but intuitively you can still try it now itself. Think about where are the odd faces. Observe that every odd cycle of this graph, it can't just be not using any of those edges that are utilizing the flexibility of the projective plane, right? Because if you just look at that part, all the faces are even. That's a bipartite graph. There are no odd cycles there. So if you take any odd cycle, it will have to utilize the flexibility of the projective plane, which is to be able to go to the antipode. But then if one of the odd cycles uses it, you can convince yourself that any other odd cycle that uses it will intersect the first odd cycle in some vertex. Okay, so that's sort of what happens, but I'm not going to convince you. You can try to convince yourself, right? So convince yourself later, and it will require you to do something with the projective plane, right? Okay. And this is basically what, so this is actually what Kawarabayashi and Ozeki did. They actually proved that in some sense, all the odd-intercyclic graphs, in some sense, this is actually if and only if. But for that, the other direction, you need some connectivity conditions, right? And because of their result, it turns out that if you just wanted to recognize odd-intercyclic bricks, turns out that could be done in polytime. The problem is, solid is not the same as odd-intercyclic. Solid cares about conformality. And therefore, the result of Kawarabayashi and Ozeki doesn't actually show that our problem is in NP or in P, right? But if you forget the conformality, then actually it would be fine. That's, yeah. Okay. Make sense? Anyways, in general, I think topological graph theory is a fascinating subject. I don't know if our lab even has a book on topological graph theory. Do we have any books? Can you please check it?
One about planar graphs.
No, not planar. Beyond planar. I think we should at some point buy Mohar and Thomason. I think it's a good book to have. At least for those of you who are interested, it's probably good to have such a book and try to learn a little bit. I never did it in my PhD days. Too late for that now. But I would strongly encourage picking up some topological graph theory if you can, and maybe teach me at some point because I don't know much, as you can tell. Yeah. What I want to show you now, really quick, is the dual of this fellow, which is drawn in Bondi-Murty. So don't look at it. So I'll draw it. So let's draw the dual of this graph, right? So now we are drawing the dual in the case of the projective plane. Okay, so we are going to have all of these are faces because remember these are actually edges. Okay, so all of these are faces. How many faces? 10 faces. Right? Now let's draw the edges. Now we need to we need one edge crossing each edge. Right? So we also need, this is an edge of the graph. So we need to go from here. This is the same as this and it will come here. Let me call this E1. Then we have an edge E2. This is the same as this. It will come out here. And we have an edge going from here, E3. This is the same as this. It will come out here. Try to figure out what this graph is. Maybe you already know. If you have a guess, raise your hand. Find a triangle. Triconus triangle. It's a graph on 10 vertices. Every vertex has degree 3. Can you find any 3 cycle? Can you find any 4 cycle? If you can't find a 3 cycle and you can't find a 4 cycle and it is a simple graph, then it is a Peterson graph. Yeah, you don't need to check isomorphism. Just convince yourself there is no 3 cycle, there is no 4 cycle. This is the Peterson graph. It is the dual of the projective planar embedding of K6. And that is what appears on the cover page of Murty. Yeah. So we did the whole course without knowing what the cover page is. Okay. Good. Yeah. So this is basically the point I wanted to make. That the conformality is what makes this problem really hard in some sense. If you throw away the conformality from the odd bicycle then apparently the problem would be in P. So you can recognize odd-intercyclic bricks in polytime because of the result of Kenta, Ozeki and Kawarabayashi. But because there is a conformality, we don't know how to solve the problem. Yeah. Not that I really understand the Ozeki-Kawarabayashi result. I don't really understand it. I've never tried to read it, but apparently it would imply that the problem is polytime if you throw away conformality. Okay. Good. What's next? So I want to just tell you a little bit of the history. So in Lucchesi-Murty there are 1 or 2 sections that describe families of families of solid bricks that are not odd-intercyclic. Right. Yeah. For example, the Murty graph is the smallest solid brick that is not odd-intercyclic. In the same spirit, they have given descriptions of 2 families of solid bricks that are not odd-intercyclic. I think one or both of these families were probably discovered by me at some point using computation. They mentioned that. And in fact, in one of our joint papers, LCKM 2018, we conjectured that for cubic bricks, it could be the case that it is solid if and only if it is odd-intercyclic. That conjecture is false. Even for cubic bricks, this is not if and only if. There are cubic bricks. I think I even remember the drawing of the smallest cubic brick. Let me just draw it for you. This was there's a group of authors from China. I don't remember all the names. I think Fu Liangru is probably one of the authors. They gave the following graph. This, I think, is the smallest cubic brick that is solid but not odd-intercyclic. Can anybody find an odd bicycle? See if you can find an odd bicycle. Yeah, can you find an odd bicycle? And is it not conformal? Not conformal, right? Yeah? Okay, let's see. 1, 2, 3, 4, 5. I think this works. This is an odd cycle, and symmetrically I can find one more odd cycle. 1, 2, 3. Is this odd cycle?
It is, but it's not.
Okay, it's not symmetric, fine. But this is odd cycle, right? We found an odd bicycle, two vertices in odd cycles, but you can see when you delete the vertices, you are left with these two vertices. They are not adjacent, therefore this is not a conformal odd bicycle. This is an odd bicycle. And it turns out that this graph, every odd bicycle you will find will not be conformal, right? And anyway, so this was due to some 4 authors, I think. I don't remember the name. Maybe they have said in the book. Let me see. Yeah, I don't remember. Anyways, fine. So this was a conjecture that for cubic bricks we thought solid was if and only if odd-intercyclic. You can see there is a small counterexample, 12 vertices. It's not that big. I could have easily found it using computations, but I did not. So, therefore, the conjecture was false, and it was, I think, found to be false within the next year or something, like within 6 months of the paper, like, hey, false. So, next time you put a conjecture on a paper, make sure you check it using computations carefully, right? Don't be lazy about computations like I was. Anyways. Yeah, so I think we can take a break around this point. I want to tell you in the remaining part of the lecture, we'll start within 5 minutes because I don't want to take too long, because we also have to finish by 4:45 or 4:50. There's a class here at 5 o'clock, right? So let's try to take a short 5-minute break, and then I want to quickly tell you about a related problem and sort of try to find a way to connect this part of the course to the next part of the course through that problem. Yeah? Okay, thank you.